In this video, we're going to talk about a strategy for calculating orders of permutations. So let's suppose, again, I have some sigma, which belongs to S sub n, and let's say I've written sigma as a product of disjoint cycles this time. So not just any cycles, but disjoint cycles. So several cycles here, A21 through A2, K2, and then on through AM1. We'll have M cycles altogether. And the cycle lengths, as usual, will be K1, K2, up through Km. In fact, the length of the cycle this time are going to be very important, so let's write those down. So this is a K1 cycle, this is a K2 cycle, and so on, up through the last one, which is a Km cycle. And let's suppose I want to find the order of sigma. Well, before I do that, I want to just think about the following more elementary question. What is the order of a cycle? So let's suppose I have a single cycle written down, and I want to find its order. That is, how many times do I have to compose this thing with itself before I get back to the identity? So to figure this out, I'm going to use that more visual way of thinking about cycles that I introduced in a previous video, which is to write down all the elements in the cycle all the way up through A1, K1. And then back here. All right, so we have a mapping. A11 gets mapped to A12, which gets mapped to A13, which gets mapped to something else. And then something else gets mapped to A1K1, which gets mapped back to A11. So that's how this cycle behaves. That's how this behaves as a function on the set 1 through n. All right, so how many times would I have to compose this function with itself to get back to the identity? Well, one way of thinking about that is just, let's call this alpha. Maybe I should call it alpha 1 since it's the first cycle in my representation above. And let's just think about, what do powers of this cycle do? So first of all, what does alpha 1 do? Alpha 1 to the first. Well, it does exactly what's shown over here. Nothing that surprising there. But what does alpha 1 squared do? Well, let's just think about how alpha 1 squared would act on elements of this set. So I know that alpha 1 maps A11 to A12. But what would the square do? Well, the square means I'm going to apply alpha 1 and then apply alpha 1 again. So what does that do to A11? Well, applying alpha 1 the first time takes us to A12, and then applying alpha again takes us to A13. And if I start at A12, well, alpha squared is going to take this to A13, and then again to A14. So alpha 1 squared just advances each element by 2 positions along the cycle. Along the cycle shown there. Okay, what about alpha 1 cubed? Well, it's going to advance each element 3 positions because each time I apply alpha, or alpha 1, I'm advancing this element 1 more position, 1, 2, 3. Well, and so on. Okay, so how long does it take to get back to the identity? Well, I need to figure out a power of alpha 1 that's going to take this and advance it all the way around the cycle. Well, the total number of positions I would need to advance in order to make it all the way around is the same as the total number of elements in the cycle, which is K1. So alpha 1 K1 would be equal to the identity, which in this group I'm calling epsilon. And that's the first positive power of alpha 1 that's going to get us there, because any smaller positive power is going to take A11, for example, and move it part way around the cycle, but not all of the way, which means it's not going to fix A11. The identity is a permutation which fixes everything. So if I have an element which is not fixed, I know that's not the identity. That permutation is not the identity. So this means the order of alpha 1 is equal to K1. And similarly, for each, let's call them J. For each J, the order of alpha J, if this is alpha 1, alpha 2, etc., the order of each alpha J is going to be K sub J. Okay, so now how do we figure out the order of this entire thing, this sigma, which is a product of a bunch of cycles? So let's come down here. I'm going to write down sigma again. Sigma is A11, etc., up to A1K1, A21 up to A2K2, and so on, all the way out to AM1, up to AM/Km. So the total number of cycles, as always, is M. And each cycle has its own length, which we'll call K1, K2, up through Km. Okay, well, one thing that I know is because I'm assuming these are disjoint cycles, and that assumption here is important, I know that if I take any power of sigma, and I want to avoid n because I'm in S sub n, n already means something, but let's say I just take some power, let's call it just p. Usually I use p for a prime, but here I'm not assuming p is prime, it's just some positive integer. Sigma to the p is going to be this product, alpha 1, alpha 2, up through alpha m, raised to the pth power. And because, and only because these are disjoint cycles, and because I know the alphas commute with each other, I can rewrite this as each cycle individually raised to the pth power. This is because all the alphas commute. And I also know that each of these powers here, alpha 1 to the p, alpha 2 to the p, all of these are acting on different elements, that is, disjoint subsets of elements of the set 1 through n. Okay, so I want to establish two things here. I want to establish that there is a power of p, which will take this entire thing to the identity. And I also want to establish that I know what is the smallest power of p that does that. So first of all, I claim that any multiple, common multiple of k1 through km will take sigma to the identity. And I should be a little bit careful about what I mean by take. Any common multiple of this, of these numbers, as an exponent. There we go. Okay, more precisely, what I'm saying is if p is divisible by all of these numbers, k1 through km, then sigma to the p is going to be the identity. And that is not too hard to show at this point because, well, what would sigma to the p be exactly? It's going to be alpha 1 to the p, alpha 2 to the p, and so on. And one thing that we've established is that if p is divisible by the order of a group element, then that power of that group element is going to be the identity. So that means that this is going to be the identity because k1 divides p. The order of this cycle divides p. This will be the identity since k2 divides p. And I can keep going on through here. Everything's going to turn out to be the identity because the respective order of that cycle divides p. In other words, p is a multiple of the order of each cycle. So each one of these powers is individually going to resolve into the identity, which means this whole thing is the identity. Okay, so that means that sigma to the p is the identity, and therefore as long as I know this exponent is divisible by all of my cycle lengths, I'm going to get the identity back. Okay, but how do I know that that's what's required? Like, how do I know that there's not some other way for sigma to the p to be equal to the identity? So that's my other claim. So I'll put this one in red. So my other claim is that if sigma to the p is the identity, then p must be divisible by all of those cycle lengths. And here's the proof of that. So let's suppose that p is not divisible by all of them. Suppose that there is some k sub j that doesn't divide p. All right, for some j less than or equal to m, the number of cycles. Okay, so let's suppose there's a k sub j that doesn't divide p. Well then what does this cycle a sub j, or alpha sub j to the p do exactly? Well, because p is not a multiple of the cycle length, this power, the pth power of alpha sub j, is not going to be the identity, and that's because the order of that cycle doesn't divide p. And one thing that we proved is that for a power of a group element to be the identity, that power has to be a multiple of the group element's order, and in this case it's not. Okay, so in other words, I know that alpha sub j to the p non-trivially permutes the elements. Sorry, my pen's skipping. Permutes the elements. Well, which elements? The ones that belong to the cycle alpha sub j. So those would be a sub j1 up through a sub j kj. So it non-trivially permutes those elements, meaning that at least one of these gets moved to something else. In fact, it's going to turn out that each of them gets moved to something else. And since none of these elements appear in any of the other cycles, alpha sub 1, alpha sub 2, up through alpha sub m, any of the ones other than alpha sub j, the powers alpha sub 1 to the p, up through alpha sub m to the p, excluding alpha sub j to the p, don't move any of those elements. The upshot of which is if I have this permutation, sigma to the p equals alpha 1 to the p, alpha 2 to the p, up through alpha m to the p, and in here somewhere I've got an alpha j to the p which is moving somebody, like moves this element for example, then, well, first of all, that element's going to move to some other element of this set, and none of the other permutations that come after it in this sequence are going to move that element back to back to where it came from. Going to move that element in here back to a sub j1, which means sigma to the p is going to move, not fix, a sub j1, which means sigma to the p can't be the identity. All right, so what I did was I actually proved the contrapositive of this claim. I said if sigma to the p is the identity, then p has to be divisible by all of these numbers. And I said, well, suppose that that's not the case. And I showed that sigma to the p is not the identity, because whichever cycle length does not divide p is going to correspond to a cycle, the pth power of which is not going to be the identity, which means it's going to move something, and that something that gets moved is never going to get moved back to where it started, which means we can't be talking about the identity permutation here. So what that means is that altogether, let's just take a look at what we've said. The only powers which move a group element, trying to get the whole thing in frame here, I think that's enough. The only powers that move a group element back to the identity are going to be those that are common multiples of k1, k2, up through km. And that means that the order of sigma is the least common multiple of k1, k2, up through km. And that's an important result that we're going to use to find orders of permutations in S sub n.